Hi everyone, we are group 3. In today's topic, we are going to talk about an event that happened in 1983, the crash of Korean Airline Flight 007. So in order to let you guys get the point of this event, we will show you a short video first. But I have to say sorry first because the subtitle is in Chinese and also the video quality is not very good. So maybe you just get something point from the video first.
Being turned deadly. 1 a.m. After stopping to refuel in Anchorage, Alaska, Korean Airlines Flight 007 departs on the second leg of its flight from New York to Seoul, Korea. The shortest route to Seoul would have taken the jet over Soviet territory. But due to the tension between the Soviet Union and the U.S., commercial aircraft routinely flew just outside the border of the vast USSR. 10 minutes after departing Anchorage, KAL-007 starts drifting off course. 80 minutes later, the plane is no longer in contact with Alaska's air traffic control and is following an entirely new path. It is heading straight for the Soviet military base on Kamchatka Peninsula. KAL-007 is now out of range of any of the North Pacific radio beacons. The plane misses its first checkpoint, designated Bethel.
After it passed Bethel, which it missed by only 12 miles, not really enough to give the radar controllers, even had they been watching, much of a heads up. There are no more beacons on the entire North Pacific route until you get to Japan.
Kamchatka Peninsula is home to several important Soviet military installations. As KAL-007 approaches Kamchatka, the Soviet Air Defense orders fighter jets to intercept the airplane. 32 minutes later, however, Flight 007 crosses Kamchatka and re-enters international airspace. Soviet Air Defense tracks the airliner as it continues on a southwest heading. KAL-007's cockpit crew continues to make weather and location reports to air traffic controllers in both Anchorage and Tokyo, apparently unaware that they have strayed into Soviet airspace.
The passengers on that airplane, even the crew, in all probability, weren't even aware that they had ever violated Soviet airspace.
Soon, 007 approaches Sakhalin Island. Within minutes, the airliner will again be in Soviet airspace. The Soviet Defense Command orders MiG-23 and Su-15 interceptors into the air. For 20 minutes, the fighters shadow 007.
The Soviets had launched aircraft out to meet the intruder, came around behind it, and followed it across the island.
At 3:15 a.m. local time, the jumbo jet pilot requests permission to climb to 35,000 feet. 3 minutes later, Su-15 pilot Lieutenant Colonel Gennady Osipovich receives orders to destroy the aircraft. Osipovich fires his 2 missiles, each bearing 70 pounds of high explosives.
So I think the video is quite clear to understand. Maybe it is the end of the presentation. Thank you. No, I'm just kidding. I will start to tell you the whole process of the event. Okay, so this event happened during the Cold War. We know that there exists a weird phenomenon between the Soviet and the USA at that time. So it's the reason to cause this tragedy actually. So in 1983, a Korean aircraft 007 is on its way from New York to Seoul, but it deviated from the original scheduled route. So when it flies through the airspace of Soviet, the Air Force of Soviet considered it was a spy plane from USA. So they tried to warn the Korean plane and check the identify, because they want to make sure that if the plane belongs to USA or not. But the Air Force didn't get any response from Korean plane that time. Finally, they confirmed that it was a spy plane and shut it down. So from the video and the picture just I mentioned, we can know that the plane deviated from the original route more than 7.5 miles. For precisely numbers, maybe it deviated from 220 degrees southwest directions to the 245 degrees. It caused them fly through the airspace of Soviet tribes. So why they didn't notice about these big problems? Also, in every plane, we know that they equip the inertial navigation system. What's the main reason to cause this tragedy? So we know that the navigation system, inertial navigation system, is a high precision system. Include 3 separate computers connected to a precision gyro stabilization platform. Each movement of the aircraft is sensed by a gyro, and each of the 3 computers is calculated separately, then correspond the change in latitude and longitude. And also, these 3 computers constantly calculate from each other to ensure that their calculations are consistent. So therefore, the system will provide a correction function and accurately locate the actual position. And throughout the flight, the pilot also can see their latitude, and the other lights are positions on the digital readings of each computer to know their locations and the accurate locating. So in addition, the pilot also can enter their entire flight path into the inertial navigation computer, allowing them to provide a streaming command autopilot to create a fully automatic navigation system. So the pilot will have the choice to choosing the mode they need by adding the autopilot mode selector, just like the figure 2 shows in here. You can choose the mode that you need. So what's the condition to start an autopilot? Actually, there exists 2 conditions for it. So the first condition is that the lateral distance must be within 7.5 miles between the aircraft and the nearest point on the route. So it means that the distance should be less than or equal 7.5. So as long as the aircraft has 1, 2, 3, 4, 5, 6, 7, or even 7.5 miles route and land, the condition will be allowed to enter. So once this logical statement is evaluated, and then we're going to the next step, a true or false decision will be made. And what about the second condition? Is the determine which flight directions the aircraft is heading toward, because if any of the conditions are wrong, we must wait until the systems adjust to the correct. But this leads and very interesting questions, just like when we are waiting for it, what the system will do. And according to this system's internal logic, the autopilot will stay in a waiting state. We call it the inertia. Yeah, we know that. What is inertia, right? So inertia will depend on the acceleration of our gyroscope, because of the weather change may make the heading calculation incorrect. Just like the figure 3 shows here, because it may caused by some weird factors, maybe it's the weather or some environment factors. So also from the figure 4, we now know the actual distance between the aircraft and the flight path. So when the pilot switched to inertial navigation mode, it was already exists more than 7.5 miles. Yes, it means that it's already too late. So the first condition is wrong. It may cause the calculation errors. So as we can see, the pictures above shows in the interface function of the navigation's instrument, and each navigation device is attached to the various parts of the aircraft. So when using the GPS and ADF, the flight crew will know the current position and the direction of the voyage, and reporting to the air traffic control (ATC) to request a landing permit. And the function of the VOR and the DME, distance measurement equipment, shown here, is to confirm the final path position by the radar scanner, and the signal positioning before the final descent. So in the part of landing, the distance between the track mark and the track distance is measured by the MB, marker beacons, and the ILS here. Instrument landing system is a system for landing, yeah. So the ground landing system transmit a signal to sense the actual position of the aircraft, and land carries out the descent radius calculation and heading estimation to facilitate the landing of aircraft. So as you can see, there is really complicated encryption for the landing from the land to the aircraft, or even from the aircraft to the land. So it's really complex. And how about the inertial navigation system? I think everybody knows this very much, and it provides the pilot with the precision navigation data reference to latitude and longitude. So accelerometers and gyros will calculate the linear degrees of the freedoms, velocities, measure the movement in the 3 rotational degrees of freedoms to form the inertial navigation systems. And also there are 3 linear degrees of freedoms, like X and Y and Z, to specify positions. So there are 3 angular degrees of freedoms of pitch, yaw, and rolls to measure the altitude. Yes, in a different angle. And inertial navigation system, you will use a gyroscope to rotate a high speed, because actually because the gyroscope has a large inertial, and it is not very easy to be changed with the movement of the aircraft, because we know that when the aircraft is flying, maybe there will be some big movement, and it will affect the position's result. And you can imagine that it is the same as a reference point in the space, and then calculate the current position of the aircraft. And it is also an autonomous system that does not require operating on ground stations. So it's the special one of it. And let's talk about the INS. We know the INS consists in just like the IMU and the instruments, both electronics and the navigation computers to calculate gravitations, accelerations. So the IMU typically contains the 3 orthogonal red gyroscope and 3 orthogonal accelerometers to measuring the angular velocity and the linear accelerations respectively. So in these computers also, it will integrate the net acceleration to maintain an estimate of the airplane's positions. So the next part is about the sensors. As we can see, there are 2 different sensors. One is the accelerometers, and the other one is the ray laser gyroscope. And about the accelerometer, it can detect the magnitude and the directions of the proper accelerations as a vector quantity. And also, it be used to sense orientations because of the direction of the weight change. And then however, the other one, the RLG, it consists of a ray laser having 2 independent counter-propagating resonant motors over the same path. So the difference in the frequencies is used to dictate the rotation. So they mainly in focus on the different aspect for them. So then use the acceleration to us. Then we'll use the acceleration to update the velocity from the previous step to get the altitude, speed, and the precision of the aircraft. So in these pictures we can see the just like this seems like the triangle. Yes, it shows the VOR ground stations as emit a 108 Hz signal from the ground to locate the aircraft signals, as shown in the figure. As we can see the figure, more than 2 launch pads triangulate to obtain the aircraft's positions, so that we can know when they emit the signal, we can know the truly precision of the aircraft. So this is why the high frequencies method is used for the positioning, which can avoid obstacles on the ground or other signal interference. So you use this idea to avoid the obstacles. And about the final part of the introduction, we know that the ILS is the landing system, right? And it's really easy to understand the ILS sends through the radio signals, and it will evaluate the aircraft's heading, speed, and the ground altitude to determine a better landing route and returns it to the pilots. So it will tell the pilots which is the better one, and tell the pilot every details, so that it will have a better performance of the landings. Applications. In this part, we are going to introduce the INS systems which applied on the aircraft through the virtual flight. So we divided our application into 3 main parts. The first part, we are going to introduce about when the aircraft is going to take off, what the things that the air crews need to do or need to focus on. And the second part is when the aircraft during the flight, they may face some problems or affected by some environmental factors. So what should they do? And in the final part, we were going to introduce about the landing, what's the tips that they need to be focused on or cared about. The first one, inertial precision input. Before taking off, the first step is input the inertial precision in order to start in the INS systems. Just like you can imagine that when you are playing a game, there is a start point in the game. It's the same meaning of it. So it's a very important part before the flying. You have to set the inertial precision input. Alignment. This function just like to making sure there's a relationship between the INS body frame and the local level. So also there is a point that you have to be sure that all of the engines should be off. Alignment performance index. It is usually to evaluate the alignment results of INS before taking off. And as we can see, the range of the performance index is from the 0 to 9. We can also imagine that the performance index like the error of the alignment. So if you get a higher numbers means the lower accuracy, and if you get a lower numbers, it means that you had a higher accuracy. Also, as we can see, the pictures shows here, there are 2 numbers shows in the picture. The left one means the PI index is 9 in that moment, and on the other side is 5. It means the required PI. And when the left one decreased to the 5 or under 5, maybe 4, 3, 2, 1, it means that we can do the next step before the taking off. Final step. before the taking off. Waypoint input. After doing the alignment performance index, the final step is this one, waypoint input. The aircrew need to input the longitude and the latitude of the destination, just like to set a course, set a goal that we have to reach the goal. So also it is an important part during the flight. Why it is important, I will tell you later. Oh, it's very soon. INS updating. Because when they are flying in the sky, they may face some problem, just like the PI index increasing during the flight, maybe affected by the environmental factors or other factors. So what should they do in this moment? The aircrew need to predetermine the waypoint to the INS systems to making sure they are on the right track. So as we can see the pictures, the number is increasing in that time, and so they do the INS updating, and in the final the number is decreasing. So it's when they during the flight they have to do, or they have to notice that. In the final, altitude control. It is the final and also is the important part for the aircrew, because actually many historical crashes happened in these sections. The main reason for this high damage is the air turbulence. So in order to suffer the air turbulence, there are two conditions that they must to fit with. The first one is they have to make sure the engine is off, and the second one, they have to maintain it in a low speed. I think it's quite easy to imagine that why they have to that the engine is off or in a low speed. So it will be easier to suffer the air turbulence, and landing in a safe angle through the altitude adjustment system. Then they will complete the flight. Okay, is the briefly introduced about the INS system applied on the aircraft, and I finished my presentation. Thank you.